Okay, so let me introduce the second speaker of the morning session in phenomenology session. So our second speaker is Felix Yu from University of Mainz, and his talk will be about chiral symmetry.
So first of all, let me start by thanking the organizers for the kind invitation to speak here at ICBS in Beijing. It's been a wonderful conference. And today I wanted to discuss some puzzles that I see in the context of beyond the standard model physics as a particle phenomenologist, and how I take or what my approach is to try to build the right model of nature to take into account the puzzles that we see. And so let me start with ciphers. So here's a picture of a disk that was discovered in Greece in 1908. And you can see that there's structure here, some patterns about markings arranged in a particular way. And to date, this disk has not been deciphered. You can see that somebody left it. It's a mystery. But this is a bit like what we have with particle physics today. It's not that somebody left a disk for us to try to decode, but we do have many outstanding problems in particle physics that lead us to believe and understand that the standard model is incomplete. So these outstanding problems include, of course, dark matter, neutrino masses, baryonic symmetry of the universe, strong CP. You could include the new physics flavor problem, that need to be addressed by the next theory of nature. And in order to do that, we would typically add new dynamics and new degrees of freedom. And today, what I want to do is I want to explore some of the rules for model building in a way such that I can illustrate different paradigms about how we approach physics equations. And one of the most important aspects of this is that I want to break rules that are normally kept sacred in terms of model building, but I'm going to break them carefully in a way to learn something new and fundamental, in particular about quantum field theory. So to start off, this is a slide that presumably needs no introduction. The standard model of elementary particle physics is now complete. We've had the Higgs discovery in 2012, and throughout the history of 20th century physics and also into the 21st century, we've had many Nobel Prizes awarded, in particular for some of the luminaries that were here, that are here in the conference, like Sam Ting. And on the corresponding side, besides just the particle content, we of course have the standard model Lagrangian, which I've taken the liberty of adding a right-handed neutrino field with regenerations. And knowing the dynamics of the particle content is as important as knowing the particles themselves. So as fundamental phenomenologists, we want to both describe the degrees of freedom and the dynamics of those degrees of freedom. And there are further Nobel Prizes, of course, awarded to structural aspects of quantum field theory and how we built the standard model, including David Gross, of course, who's also a luminary attending this year's conference. So the fundamental question we have in Beyond the Standard Model Physics is asking, what is the new physics Lagrangian? We have many, possibly infinite possibilities to consider. And in principle, whatever new physics Lagrangian we write down, we could study one at a time. However, this is in principle, this is a practical impossibility to study perturbative calculations, parameter scans for every concrete new physics model one at a time. Instead, going beyond, we want to understand how to capture classes of models and how do we classify paradigms of such models. And one of the most powerful tools we have in modern particle physics phenomenology is to do this from the point of view of effective field theory. And simply stated, scale separation gives us a framework to capture wide classes of UV completions to the standard model. But what I want to do is I want to distinguish decoupling standard model effective field theory or decoupling degrees of freedom that follows that versus what I will call non-decoupling new physics. And if you want more technical language, I'm going to discuss non-chiral standard model UV completions versus chiral UV completions. And today, the focus is going to be on chiral of this. And the reason, for those in the audience who want an introduction to chiral symmetries as minimal fermion representations in 4D spacetime can be assigned a distinct eigenvalue of the gamma 5 matrix, and so they can be considered as either left-handed Weil spinors. And given that, we can assign distinct U1 charge gauge representations to left-handed and right-handed fermions, and in this connection, if you assign left and right-handed fermions with different gauge charges, then the fermions are necessarily massless. And this is one of the features that we have in the standard model. We can also demonstrate that each fermion contributes to current non-conservation at one loop, and this is, of course, the famous Adler-Belyaev anomaly. And it is known that anomaly cancellation is a necessary and also non-trivial consistency condition for gauged chiral symmetries. And we're going to use this extensively in the second part of the talk. And it is also very interesting to remark that 't Hooft anomaly matching ensures that anomaly cancellation is preserved no matter what scale you study the theory at, so it somehow transmits itself even across effective descriptions. And as an aside, you've probably heard in your beginning particle physics classes that the standard model fulfills this condition generation by generation. Having understood basic aspects of what a chiral symmetry is, I'm going to make the connection to the fact that several open problems in BSM physics stem from the chiral nature of the standard model. And the first is the fact that the gauge hierarchy is also related to the fact that the Higgs constant of the standard model is completely minimal. And this is something that is a puzzle, and it's borne out by our current measurements of LHC, Higgs measurements, but using such a minimal content is one of the tools that we have about looking for extensions of the scalar sector and why the Higgs is so elementary. These are two sides of the same coin. The new physics flavor problem also is a fundamental question about what the flavor structure of the UV completion of the standard model is and why that UV completion somehow knows about the flavor construction of the standard model is perhaps the biggest problem we have with regards to constructing new beyond the standard model physics, as you may have seen in John Judic's talk from a couple of days ago. The baryogenesis problem, the neutrino mass problem are also flavor aspects of the standard model that would not be there if we had more relaxed rules about how to accommodate standard model fermions and their CP violating phases. And then one thing that I'll especially focus on is the strong CP problem, which is one fundamental aspect of reshuffling UV CP violating phases in the standard model to accommodate all the possible CP violating operators we can construct in a low energy description. As an aside, one of the most popular extensions of the standard model was to construct the minimal supersymmetric standard model, which we have not seen any evidence so far at high energy colliders. But the MSSM is also built on the chiral structure of the standard model in embedding all of the chiral matter into chiral superfields. So chiral symmetry does give us many clues, and I'm trying to use this as a guide to figure out how to build extensions in four-dimensional spacetime. On the other hand, the chiral symmetry nature of the standard model also allows us to make categorical statements about what types of new physics models are allowed and disallowed, and therefore have widespread phenomenological use. On the right, I'm showing the CMS, the latest state of CMS measurements of the Higgs couplings to the elementary particles of the standard model. And you can see it follows the prediction of the standard model precisely. Everything lies on this diagonal line. And this is entirely predictive in the standard model because of the chiral structure. And it also allows us to make an exclusion on a fourth chiral generation at the categorical level. So we don't need to look for more generations of the standard model in terms of its chiral structure. What we can look for are vector-like extensions, but not new chiral extensions. And this type of non-decoupling in terms of low energy Higgs physics is what we're going to revisit in terms of how they play a role in in chiral new physics models in the effective description. Another aspect of chiral symmetry, of course, in the standard model is this mystery with the quarks to meson duality that we have in QCD. And this is captured by chiral Lagrangians. And you may remember there's a famous U1 problem from meson spectroscopy about the scale separation between the eta prime mass that was solved by the U1A anomaly by de Hooft. And on the other hand, you can also revisit this question and try to study phase counting, and you will see that there's a strong CP problem, which we cannot immediately satisfy given the strong constraints on the NADM. So along those lines, we're going to study effective descriptions, non-decoupling theorems, and the specific paradigm where new physics is chiral and when new physics chirality is orthogonal to standard model chirality. So I want to explore the interplay between a misaligned Higgston unbroken phase in these two chiral symmetries. And I want to use this as a model building principle for new physics extensions. And so the first aspect of today is going to be looking at the strong CP problem and constructing non-vanilla axion solutions, aka studying global chiral symmetry extensions of the standard model. And the second thing I'm going to discuss are Z-prime physics and the collider phenomenology, where I'm going to find some novel field theory results based on a gauged chiral extension of the standard model. So first, a quick refresher on the strong CP problem. Our search for the neutron electric dipole moment indicates the absence of CP violation in strong interactions. This was done back in 2020 by the NEDM collaboration. When you translate the constraint on the dipole moment of the neutron into the fundamental standard model parameters, you find you construct theta bar, which is the theta of the QCD interactions plus the argument determinant of YUYD. You get a severe constraint that the magnitude of theta bar should be less than the order 10 to the minus 10. And this gives rise to a naive, a fine-tuning problem or a very strict problem about the aesthetics of the fundamental parameters, given the fact that we expect the two independent sources of theta bar to be uncorrelated. Traditionally, there are three classes of solutions. If you're interested in reading about them, I wrote a quick primer in 2023, but today we're going to focus, of course, on the most vibrant class of solutions, which are Petri-Quinn mechanism and the QCD axion. And the way this works is that you would promote theta to be a spurion, calling the corresponding degree of freedom the axion. And you would generate the potential for the axion using the topological susceptibility to QCD, which we can denote I. The Vafa-Witten theorem ensures that the new degree of freedom settles into the CP conserving minimum. But fundamentally, and this is where we're going to connect back to effective field theory, you need the PQ current, the Petri-Quinn current, to be chiral and have a non-trivial anomaly with respect to QCD. So U1 PQ cross SU3 squared must be anomalous. And this is going to source the axion potential. So the simple construction, once you understand this field theory, the KSVZ and the DSVZ models were just the simplest realizations to make this chiral anomaly, this color anomaly happen. So you can either couple the complex PQ scalar field to SU3 via Heffy vector-like quarks, or you can couple the PQ scalar field to a 2 Higgs doublet model and then use the fact that the 2 Higgs doublet model has Yukawa interactions with the colored fermions of the standard model to realize the decolor anomaly. And so it's one of the lessons where if you recognize the field theory ingredients necessary in order for the PQ mechanism to work, you can write, if you're quick enough, you can write very straightforward model building papers to realize these mechanisms. The point here is that in both vanilla cases, the global Petri-Quinn symmetry is exact and accidental at the renormalizable level. And this, in principle, is one of the biggest problems which you've heard about with regards to axion quality, that there's no intrinsic mechanism that we can make this work for all scales. So as a refresher, I'll skip through most of this quickly. This is the field theory calculations that you have to do in order to calculate the effect of this exact runner Peccei-Quinn and global Peccei-Quinn symmetry from standard model effects. You generate the axion mass from the gluon operator by coupling it in the exponentials, for example, of complex quark masses. And the index theorem von Atiyah-Singer tells you that you can connect the PQ color anomaly to the instanton action in the 't Hooft determinantal operator. And so as long as you have an instanton amplitude characterized by this factor K, then closing off these chiral couplings of Q bar Q is going to give you axion potential. And so this is something that is called instanton flower diagrams. You get a sum over all of these, and power counting into chiral symmetry breaking parameters from the ansatz of QCD will give you the direct coupling of all of the Goldstone modes of standard model n equals 3 chiral Lagrangian with the addition of the axion. And this is something that I show here. And this is bread and butter chiral Lagrangian with axion physics. In terms of moving beyond, what I want to emphasize is that vacuum angles are intrinsically non-decoupling features in any BSM extension. And more than that, chiral anomalies always rotate vacuum angles. So I can do a thought experiment where I can consider an extension of the color gauge group of the standard model into a product gauge group of SU3 cross SU2, SU31 cross SU32. And at this scale, I would think that the high energy theory has two independent vacuum angles, one theta 1 and one theta 2. But I can further embed SU31 and SU32 into an SU6. I mean, I'm allowed to do this. There's certainly enough degrees of freedom in SU6 to have a lower energy version that has SU3 cross SU3. But knowing that the semi-simple Lie groups only have one non-trivial vacuum angle means that the vacuum angle in SU6 is inherited in this intermediate scale by theta 1, theta 2. So this is a thought experiment to demonstrate why vacuum angles are very non-trivial to think about when you start considering new extensions of the standard model, and in particular, the effect of chiral anomalies. So what we're going to do is use this intuition to bootstrap the U1 Peccei-Quinn at the Q scale into a UV completion to get non-decoupling enhancement of the axion potential. And so this UV completion is known as enhancing the axion potential by small size instanton effects. This was pioneered by Agarwal and Howe and also discussed earlier in papers by Randall and others, Randall and Georgi. But if we embed SU3C into a larger UV gauge group, then confinement of the larger gauge group can give additional instanton-induced potential terms to the light axion. We need to do non-trivial bookkeeping to trace the Peccei-Quinn symmetry from the IR to the UV. And as a practical consequence, you will also get additional signatures that result from this non-trivial embedding. So you'll get, for example, partners of the gluon that are going to be heavy that you can look for in collider signatures. So I'm not focusing on it today, but it is something that I've studied in a previous paper with Bogdan Dobrescu. So determinantal approach will readily account for small size instantons, and we can capture the explicit, the alignment of the explicit and instanton Peccei-Quinn by different pseudo-Nembo Goldstone bosons. I've already done the thought experiment of SU3 cross SU3 and SU6, and the model that we use is going to be by Gaillard and collaborators, where they took an SU6 color unified model and augmented it by an SU3 prime. This essentially, let me skip to the next slide, is going to be a KSVZ-like variant and a DFSZ-like variant to add a new contribution to the axion mass. So the field content, once you study it, is going to be very intuitive. The main point is that you get an MA squared FA squared relationship that will include small size instanton corrections to enhance the axion mass. You can make it in terms of small size instanton and also a confining gauge group lambda d. And you can grow the axion mass to be within the collider reach. So here's a plot of MA versus GA gamma gamma in this model from Gaillard and collaborators, where the MA-FA squared are these dotted dashed or dot dashed lines for different choices of the underlying parameters, where we can push the axion to be in the TeV scale, which could be realistically seen by either current LHC experiments in the gamma-gamma channel or by future colliders at higher energies. One nice feature is in these models, because you have an extension of the fermion content in these new color extensions of the standard model, you also get a axi eta in addition to the high quality axion. So you will see two different degrees of freedom that will split the topological susceptibility of the UV extension. So you have two different targets as a smoking gun signature for these UV completions. So this is SSI-driven mass enhancements, already a non-trivial way we can study chiral extensions of the standard model. What we can also do is we can do something, we can break the rules. So if you recall, one of the most tender aspects of the Peche-Quinn mechanism is the fact that the U1PQ was supposed to be exact at the normalizable level and accidental. And something that you may worry about is that the DFSC UV completion had already two incommensurate variants. You either had a cubic coupling between the Peche-Quinn scalar and HUHD, or you have a quartic coupling. But these two variants, if they're both allowed by the global symmetry, don't satisfy the requirement that global symmetry should always be accidental. And so if you turn on both of these couplings at the same time, you'll notice that your solution to the strong CP problem is going to fail. And so this is how me with a few other collaborators, so 3 postdocs, Fatime Alahi, Gili Alor, Bernajari, and then my 2 PhD students at the time, Alexei Kiva and Julian Laux, it broke the rule. Why don't we just add an explicit breaking to softly break the PQ symmetry, and this is what we call the anarchic axion. And we wanted to understand the full effective description from the soft breaking because it gave us complete control about understanding the leading Peche-Quinn breaking in terms of the axion mass, but also the nonlinear realization with axion self-interactions. So this is a slide with equations to demonstrate that we analyzed the effects of this nonlinear, this soft breaking B mu. And you can see that we get deviations from the normal MA squared, FA squared relation, not just proportional to lambda QCD to the fourth, but where we also include, for example, a V max parameter that will induce a new cosine term in its potential. So here are the summary of our results. You can see that for different choices of Vmax, what we will get is we can traverse away from the DFSC line and saturate the GA gamma gamma coupling, but have essentially we can treat MA as a free parameter by tuning, admittedly, the soft breaking term. And the soft breaking term is essentially turning off the contribution to the axion mass coming from the QCD potential, where we realize more and more accurately the intrinsic Goldstone nature of the Peche-Quinn axion. And so this anarchic axion deviates from the DFSZ band. It's admittedly fine-tuned. You could argue that some of the most extreme choices of these parameters are even more fine-tuned than the original strong CP problem. What we wanted to really demonstrate was that the accidental nature of the Peche-Quinn symmetry is something that should be explicitly studied, and we would get deviations away from the vanilla model. So this is a non-vanilla extension where we just break the rules consistent with, and we calculate. So deviating DFSC is breaking the rule because a global chiral symmetry, you should just write down whatever you want in order to explicitly break it. And we've seen that we have diverse phenomenological applications, both with small size instantons and soft breaking of Peche-Quinn. But what I want to now turn to is how does the global chiral symmetry effective description connect to non-decoupling effects in the gauged version? So what we're going to do now is we're going to gauge a chiral anomalous current in a safe way, the effective description. So pivoting to gauged U1 chiral symmetry, the first question we should ask ourselves is which chiral symmetry of the standard model should we gauge? The standard model, of course, has a global U1 baryon cross U1L symmetry, and we can gauge any combination of B and L separately without modifying the Yukawa matrices. Recognizing the fact that there are anomalies related to U1B and U1L, the safest thing to do is to, for example, gauge purely the baryon current by itself. The baryon current by itself, we can add new electroweak fields, which we call anomalons, to cancel the anomalies. This is the field content, so they're going to be vector-like doublets under SU2, vector-like representations under hypercharge, and then gauge singlet under the standard model. But you'll notice that if you hide last column, which indicates the U1B charge, then these are just pure vector-like representations under standard model. And therefore, the last charge, which is the U1B charge, is what forces it to be chiral. Yes. Yeah, so what I mean is, if I don't want to modify the Yukawa matrices, this is a small typo, any combination of B or L, I can gauge, and the Yukawa matrices by themselves do not have to change, I just have to handle the anomaly structure. I do. So these are new fields. Unfortunately, they use the same language, but these are new fields. These are not standard model leptons. So there's no generation number, for example. So I'm using the multiplicity of the lepton fields in the standard model into the charges here. So because I want to do U1B by itself, I will introduce a new scalar field, complex scalar field phi, that is a standard model singlet, but has B charge of 3. Spontaneous breaking is going to give masses to all of these new anomalons and will also give mass to the Z prime. Now, if you write down the renormalizable Yukawa interactions, this maybe makes it clearer how the mass mechanism works. The anomalons will have two different vevs that can give mass to their give masses, Dirac type masses. So you either have phi vevs, and if I set phi to a vev, you'll notice that these are vector-like representations. Otherwise, I have Higgs insertions, and these are normal Yukawa in the standard model. So if I want, in order to make this realistic, I have to set all the Yukawas to be non-zero, otherwise I have an accidental Z2, and I would in principle have stable charged particles, but we have checked phenomenologically that I can set Y1 and Y2 to be small, and then I'm still consistent with the branching of Higgs to gamma gamma. And I'm going to consider a new physics spectrum with heavy anomalons, so I want to push all of these Y's to be order 1. I'm going to have a light Z prime, a light phi, and we're going to focus on the effective operator ZZ prime gamma in this, in the remainder of this talk. And this ZZ prime gamma vertex, of course, is very interesting in its characteristic of anomaly cancellation. So usually in textbooks, this type of vertex is studied only at the divergence level, but because we want to calculate cross sections or decay widths, we need the full vertex structure, not just the 4 divergence. And following Weinberg, and also a later paper by Davis and Sukso, whose reference I write here, we are going to allow each diagram to be shifted independently of each other by some unknown form momentum that we can parameterize in terms of the external form momenta P1 and P2. And so these constants Z and W will keep track of the anomaly for us. We can also do this calculation in dimensional regularization in naive gamma 5, and I'll demonstrate that this allows us to recover all the phenomenology of chiral anomalies without having to use complicated regularization prescriptions or with 't Hooft-Feldman. So the full vertex, just using Lorentz covariance, can be written as the sum of 8 different form factors. 6 of them are going to be finite by construction, and then I can separate the W and Z dependence into 2 quote-unquote divergent form factors, G1 and G2, where you notice that the momentum dependence of G1 and G2 is lower than the momentum dependence of F1 to F6, and that's why G1 and G2 carry the momentum dependent shift, and they're the ones that keep track of my divergence. This is an overcomplete basis. As Davis and Suxo point out, I can eliminate 2 of the finite form factors by redefining the other 6. And so this is an exact identity in 4 dimensions. And by reusing that, I can collapse the form factor decomposition into 6 independent form factors, F prime 3 to 6 and G1 prime, G2 prime. And if I just evaluate the 4 divergence of this vertex function in this ansatz for the Lorentz covariant decomposition, you'll see that you get this structure on all of the 4 divergences, where you notice, well, if you set all of the external momenta and masses to be 0, you will find you'll recover the canonical statement that you cannot simultaneously set all of the 4 divergence currents to be 0. So the way this works in practice, for a specific fermion that has our structure corresponding to ZZ prime gamma, what we can do is we can parameterize the couplings under the Z prime and the Z as vector or axial. And then you see this, the coupling to the QED current is of course purely vector-like. And so I only have either vector and axial couplings to the Z prime and Z, or vector and axial couplings to the Z and then the Z prime. And they come in these different linear combinations. And you have the canonical W and Z, W minus Z, W minus 1, and Z plus 1 structure that is familiar for anomaly cancellation. The interesting thing here is that you have a separate contribution that is also proportional to m squared times the scalar Passerino-Veltman function C0. And this is hopefully familiar from Higgs physics, because this is exactly the loop function that gives non-decoupling behavior of the top in Higgs to glue and Higgs to gamma gamma. So even if I sent m to infinity, this structure, which is proportional to GV Z prime GAZ, does not decouple from my vertex. Now, in the literature, usually what you'll find is that there's a fixed choice of W and Z to define either a covariant or a consistent anomaly, and they determine the corresponding Wess-Zumino effective operator. This I can go over in a backup slide if people are interested. But what we want to keep track of is the fact that this W and Z should be unphysical. Nature should not know how I chose to do my loop momentum calculation. And one fermion at a time, I'm going to get a W and Z dependence. And if I keep this W and Z dependence throughout the calculation, what I can do is I can require that the total vertex function should be W and Z independent. And if I do that, then what I'll find is that this requirement is equivalent to summing over fermion content that satisfies chiral anomalies. So this is a reformulation of chiral anomaly cancellation to make this vertex function be W and Z independent. And it's a new prescription that we're excited about or introducing, for example, for next to leading order lecture weak corrections, where in principle, if you use a specific W and Z prescription or a specific 't Hooft-Feldman scheme for gamma 5, then in principle, you don't know that you've gotten rid of the anomaly with your fermion content. But if you look at this expression for the decay width, exotic decay width of the Z to a Z prime photon, then this first line is the sum over all the standard model field content. The second line is the sum over all the heavy anomalon field content, but there's no W and Z dependence in this overall expression. This is very exciting because in exotic Z, decay is emblematic of gauged E1 prime extensions. And here I'm showing the branching fraction of the Z decaying to Z prime plus photon. You can see that this tends to, so this turns on, self-consistent with Landau-Yang theorem, from zero branching, from zero width, and it turns on and has a slight cusp here. This is when the internal anomalons become heavier than half the Z mass, and then it smoothly falls off. The different colored lines correspond to different choices of my GX gauge coupling. And for different, some of these parameters were already tested by the L3 experiment from LEP, where they searched for a dijet resonance plus a photon recovering the Z mass. And so you can see the LEP exclusion here excludes some region of Z prime mass and gauge coupling of 1. But for most of this parameter space, you would be at the level of 10 to the minus 5, 10 to the minus 6 in exotic branching fraction. But the point is, because there's a non-decoupling effect for these heavy anomalons, there's very little other dependence besides the gauge coupling and the mass of the Z prime, because we're in a non-decoupling effective description. So U1 prime gauge extensions can be tested by a suite of exotic Z decays to make categorical statements about chiral extensions of the standard model. And this is particularly exciting because we're in an era where we're considering future E plus E minus machines, such as CEPC and FCCEE, and they'll be crucial for testing new chiral dynamics. So here is a rescaling of the LEP3, sorry, the L3, not LEP3, the L3 exclusion to a Terra Z rescaling. And we did not do anything beyond just a simple rescaling by statistics, but we're currently working on an actual Monte Carlo evaluation of exotic Z decays to test how a Terra Z factory would constrain exotic Z decays in all the different flavors and variants of Z prime models that we want to consider. I can also mention that in the past, I've worked with some faculty here in Beijing, Jia Liu and Xiaoping Wang, where we studied we studied kinetic mixing and dark matter production, also relevant for for production of new light degrees of freedom at CEPC or FCC energies. And this is one of the additional motivations for these new colliders. So I'm already going to the conclusions. So effective descriptions of chiral new physics carries a rich phenomenology and field theory structure. I've highlighted two manifestations of this idea. The first are non-vanilla axion models that expand the discovery potential for strong CP solutions. The second was in the gauged version, where we studied the effective operator construction of ZZ prime gamma, and we formulated a new way to consider chiral anomaly cancellation. In many open questions and motivations for BSM, I can readily admit that it's crucial to both create and test new paradigms, but this is where we're in an era where theory, of course, always works hand in hand with experiment, but the main point is that creating and testing new paradigms is the theorist's job. The experiment needs to come and tell us and give us guidance about how to make progress. Fortunately, we're dealing with big and fundamental questions where we need experimental data to make progress. And I would say the best data is yet to come, especially because CEPC as a new international flagship would provide some of the most important and groundbreaking data to answer some of these fundamental questions we have about the standard model. And as a final note, I've always believed, as an American physicist working in Germany, and here in China, that science transcends barriers. And so we should all strive to have a future where the international cooperation transcends any other barriers or any other obstacles we have for the pursuit of science. So thank you.
Thank you for your talk. Any questions?
Say, gauging of Pei-Quinn symmetry, does it lead to?
Yeah, so I did not gauge Pei-Quinn because
I
then,
understand.
yes.
Pei-Quinn symmetry still keep axiom, well, like an axiom that's not there.
Yeah, so this is something that I actually want to, I don't know the answer. This is something I want to study. I want to distinguish the non-decoupling behavior that I see for these heavy anomalons with the instanton-induced axion potential. Because something that always bothered me was the statement that if you have a chiral anomaly, your theory is A, not normalizable, and B, that you would generate a mass for the Z prime, right? With the usual 3-loop calculation that people sketch. Right? The point is, especially for U1, I can add a gauge invariant mass from Stuckelberg, right? And the question was, what is the distinction between a Stuckelberg mass and an anomaly-induced mass at this 3-loop level? I don't know if anybody's actually studied or answered that question. And that would provide an avenue in order to understand what is the fundamental gap in the theory between a anomaly-free U1 theory in the gauged case and the global case when I turn on an anomaly. Because the anomaly in Z prime, in principle, turns on the mass or the Z prime. The anomaly in the global case turns on the mass for the associated axion. And the question is, are those two actually one-to-one? Right? The explicit breaking that you get from the anomaly, is that the correspondence that I would see in the longitudinal equivalence? But it's something I don't think people have actually calculated.
So in the axial model, you embedded the SU3 to a higher group. So what happens to the extra gluon?
So the extra gluon, in principle, it lives at the V diag scale. And this is in the this is in the breaking pattern coming from the fully unified color unified theory. I confine, so some lambda color unified theory, so SU6 cross SU3 prime becomes SU3 color times a diagonal subgroup that combines SU3 prime with a SU3 subgroup. And then the V diag would vev all of these degrees of freedom. So I'm only left with SU3 color. But in principle, already from here, you would get some multiplet structure for gluon partners that live at lambda cut. And those, if the lambda cut scale is low enough, you would see as heavy partners of the gluon.
So how heavy it is?
In this model, we use lambda cut. I think that's very heavy. So we use order, sorry, let me go to it. Yeah, so it's going to be heavier. I don't have it here, sorry. We have it heavier than say 10 to the 5, 10 to the GeV. So outside the scope of high energy colliders. This is lambda diag. It's not lambda cut, but lambda cut is heavier.
Okay, then it's a way to protect the quality, right? So by raising the axial mass, you can protect the quality.
Yes. So the main reason that they use this construction with lambda, with this extra SU3 prime, is because they use the massless up quark solution to satisfy the theta of SU6 and SU3 prime.
I see.
So the up quark solution is recycled again, but the point is that the up quark belongs to an up prime and they have to make it massive. Otherwise, you'd have another goldstone at low energy that we don't see.
I see. Thank you. Thank you.
Okay, if no more questions, let's thank our speaker again. Yeah, and now we will have